given one tutorial talk on singlet fission. Just to capture the essence of Professor Michl's work for over the years, it's enormous in photochemistry and photophysics, and also in different kinds of electronic structure calculations. His roots actually originate from Czechoslovakia. He did his master's in Charles University in 1961. And then he moved for his PhD to the Czech Academy of Sciences, Prague. In 1965, he finished his PhD and moved to the States for the first time. And he occupied multiple positions in States for almost 5 years till he took up an independent position as an associate professor at University of Utah. And he had been there almost till the entirety of his major part of the career before he moved to University of Texas at Austin. And of course, and then finally taking up a professorship currently at University of Boulder, University of Colorado Boulder. He's of course associated with his home country, and he is part of the Institute of Organic Chemistry and Biochemistry in Czech Republic. The span of work and influence of Professor Michl's work has been enormous, and he has been recognized by the National Academy of Sciences in the US as a fellow. He has also been a fellow, recently been fellow of the Royal Society of Chemistry. And I would like to mention some specific things about this, that he actually won all the top awards when he was starting up as a faculty, the Alfred P. Sloan Award, and specific awards from major societies. One of them is Porter Medal, which is the Photochemical Association Prize, Society's prize, one of the highest prizes. With that, I would like to not take any more time and let Professor Michl go on with his second tutorial on singlet fission. Professor Michl.
Thank you very much for your kind introduction. I would like to start exactly where I stopped last time. The slide that you see now is just the introductory slide that has some references to review articles and to articles that contain simple introductions to the basic concepts of singlet fission and its possible application in solar cells. There are other possible applications that I'm not going to mention. And we got as far as talking about the greatest need in the field now, which is to find suitable materials that would be practical. It has already been demonstrated in the laboratory that you can get almost 200% yield of triplets, and it has even been demonstrated that you can allow these triplets to reach interfaces where they separate into positive and negative charges, and you can collect those on electrodes and actually get an increased yield of solar energy that way. But these materials that have been used are not really suitable because they do not meet the many additional requirements on top of the 200% triplet yield that are required for a practical application. And I give you the list of those requirements, and it's impressive. It's a long list. So we need some sort of general principles, some design principles for finding materials that will have all these properties. If currently we have maybe a dozen or so materials that give us high triplet yields, but we probably need hundreds of these before we find some that meet all the requirements of a practical system. So the requirements that guide us to the principles that we're looking for were briefly mentioned. I said that we need to choose the right chromophore. And the main criterion for that is that it has to have the T1 level, the lowest triplet level, located almost exactly halfway between the ground state level and the first excited singlet level, because that makes singlet fission approximately isoergic or maybe slightly endorgic or exergic. Then it can proceed rapidly. And then there were other requirements. One of them was the issue of how do we organize these chromophores in a solid? What crystal structure is suitable and what crystal structure is not good? And that has to do with two factors. One of them is we need to have a structure that promotes rapid singlet fission. But the other one is that we want a structure that suppresses or minimizes the rates of all competing processes, because what we want is a high yield of a triplet. And that does not only depend on the rate of triplet formation, that also depends on the rates of competing processes. And then there was a third requirement, which we are now also working on, but I don't really have enough results to include in the presentation, nor the time to do that. And that is, what do we do to make sure that the triplets that are generated by singlet fission actually reach the interfaces where they separate into charges, and how do we make sure that we collect the charges efficiently on electrodes? So where we stopped was a discussion of what kind of structure the chromophores need to have. From the list of properties of desirable chromophores for singlet fission, a long list, you probably remember that there were things like high extinction coefficients everywhere above the band gap, the band gap being approximately 2.2 electron volts ideally. That would mean that the triplet would have the energy of about 1.1 electron volt ideally. And there were many, many others. So the primary issue is, how do we find chromophores, typically electron chromophores, because we want these high extinction coefficients, that have the property that the gap from S0 to T1 is the same approximately as the gap from T1 to S1. And I gave you a simple argument that explains why it is that we want molecules that have a biradicaloid character. The argument is repeated on the slide which you now see, which was already shown yesterday. And just very briefly, I'll review it again on two examples. One is the H2 molecule, which is shown in this part A of the figure. You have a plot of the energy of a state vertically versus a distance between the two hydrogen atoms that form the H2 molecule, plotted horizontally. And so for the ground state, that would be the S0 curve. You have the familiar Morse curve. In the dissociation limit, you have a perfect biradical. It has two hydrogen atoms. They basically don't know about each other because they are far apart. And you have basically no difference between the energy of S0 and T1. If you bring the two atoms closer together, those levels split. The lower level is the singlet. Well, that's the ground state of the H2 molecule. And the triplet goes up. The curve is shown here in a dashed line. And then when you reach the geometry of the standard ordinary ground state geometry of the H2 molecule, that corresponds to a distance between the two hydrogens of about 3/4 of an angstrom. At that point, you have a very large difference between S0 and T1. and a much smaller difference between T1 and S1. And the curves are continuous. That means that somewhere between this limit of ordinary molecule and this limit of a biradical, perfect biradical, there will be a place, which is indicated by the location of these arrows, a place where the distance from S0 to T1 is about the same as the distance from T1 to S1. And that's about halfway between the geometry of an ordinary molecule, stable like H2 at its equilibrium geometry, and the perfect biradical. Such geometries are referred to as biradicaloid. That means similar to a biradical, but not quite a biradical. And this is a reason why that kind of structure is desirable for materials that we want for singlet fission. The other example that I mentioned was the case of ethylene, where the biradical is perfect when there is a 90-degree twist. The angle of twist is plotted horizontally, energy is again vertical, and you can see the very near degeneracy in a almost perfect biradical. And you can increase the gap between the S0 and T1 curve by undoing some of the twisting. If you go from 90 degrees to smaller twist angles, or maybe to complete planarity, you see from this calculation that you indeed increase this separation, and it becomes equal. The blue arrow showing the S0 to T1 distance becomes equal in length to the red arrow, which shows the distance or the gap between the T1 and the S1 state. Now, we then mentioned that there is an example that actually was the first example of a molecule that was proposed as being suitable for singlet fission on the basis of this very simple argument. And it turned out that it does indeed produce 200% yield at liquid nitrogen temperature, somewhat lower at room temperature. But that was one way of making out of a perfect radical a biradicaloid that has that's easily available. It actually has it's commercially you can buy it. Now let me return to this case of ethylene. This looks like plainer ordinary ethylene would be just a very good compound for singlet fission. But of course, it has some troubles, right? Because the distance between this S0 level and that S1 level is so large that it does not absorb in the visible at all, and it does not absorb in the near UV. It only absorbs at wavelengths that are around 200 nanometers or less. So it's useless for collecting solar energy. But if you could somehow manipulate the magnitude of the excitation energy and make it smaller, change ethylene chemically into a structure that actually absorbs visible light very nicely, making the compound, for example, blue, then you might have something interesting. So how could you possibly do that? What do you need to do to a ethylene or to a CC double bond to make it want to absorb light at such long wavelengths? Well, you need to decrease the HOMO-LUMO gap. How can you do that? Well, what you can use, the principle that you can use to modify ethylene is the attachment of substituents. So let's see what will happen if you use the simplest possible model for a pi system, which is the Michl model, almost 100 years old now, not quite. And let's see what that would suggest that we could do to reduce that HOMO-LUMO gap. If you consider the simplest situation in which you just look at the pi orbitals and pi electrons of the ethylene molecule, you can symbolize it as shown here. You would have 1, 2pz orbital on one of the carbons and one 2pz orbital on the other carbon, and they are about 1.34 angstrom apart, and they interact with each other. And in the Michl theory, this description of the interaction is very simple. You say that there is a matrix element of the Hamiltonian that corresponds to the interaction, and you call it ordinarily just the resonance integral, although physicists, they call it the hopping integral because it has to do with the rate at which an electron would hop from one to the other atomic orbital if you started with it localized in one of them. And you know that in Michl theory, you solve a 2x2 matrix, you diagonalize it, and you get a picture that relates the energies of the orbitals before the interaction. They are degenerate before they begin to interact. That's these two lines. Energy is plotted vertically. And after the interaction in the units of that resonance integral, beta, the split, one of the orbitals becomes bonding, stable, one becomes antibonding, and the distance between them is twice that resonance integral beta, 2 beta. So if I use beta as my energy unit, the distance is 2. And this is large enough to make the molecule useless because it only then absorbs at the wavelengths where we don't basically get any energy from the sun at the sea level. So what we could do is to modify the molecule by substitution, putting a donor substituent, that's shown in blue. So this is another 2pz orbital. The molecule is viewed from the top, so the orbitals look like circles. And also an acceptor orbital, and you attach both of them to the same center. This is known to organic chemists as captodative substitution. If this, for example, were a radical, instead of having the same thing repeated on the right-hand side, if you just had a hydrogen here, then you would have initially a methyl radical, but now a methyl radical that carries a donor and an acceptor. And that's why it's called captodative. The acceptor captures electron density from that central carbon atom, whereas the donor substituent donates electron density. And organic chemists have known for decades that that actually stabilizes the radical. Now, if we do that in our ethylene on both sides, what will happen? Well, again, we can approximate the two orbitals of the resulting ethylene by just looking at the HOMO, that the bonding orbital, and the LUMO, the antibonding orbital, that will arise from the initially non-bonding two levels that we have, one on each of these carbons. But now, with the donor and acceptor present, the coefficients will not be 1 and 1 as they were here. They will become smaller. Actually, if the acceptor is quite strong and the donor is quite strong, you end up here with an allyl radical. And you know that the allyl radical will have a non-bonding orbital, so the energy here is correct. And the coefficient on the central atom will be 0. There will be a node going through the HOMO and also through the through the non-bonding orbital. It could be a HOMO or a LUMO depending on how many electrons we put into that allyl. But the non-bonding orbital is the one I'm talking about, and it will have a node there, so you'd end up with 0. If the donor and the acceptor are not quite as strong, well, it will not be 0, but it will be somewhere between 0 and 1. So now the interaction of the non-bonding orbital of the 3-atom system on the left and the 3-atom system on the right will be weaker because the size of this coefficient matters. If it's 0, there will be no interaction. If it's 1, there was an interaction that gave us a homolumo gap of 2. If it is somewhere between 1 and 0, and the number it will actually have is shown here. These will be the coefficients on the non-bonding orbital of that allylic-like system, where D is simply a measure of the strength, the donor strength, and the acceptor strength of those two substituents. Well, then you will end up with a gap here, which is no longer 2. It is 2 multiplied by a fraction d squared over 2 plus d squared. And here is a plot of the result. Depending on what d is, that's plotted here from 0 to infinitely strong. And here would be inverse tan or arctan of a d that's plotted down here. The magnitude of the split of that band gap, the homolumo gap, that's this number here, that's as shown there. It's plotted. And you can see that indeed, if the energy that you have on the donor and the acceptor is so high that the donating orbital and the accepting orbital basically no longer can interact, it goes to infinity, you are at 2. That would be as if you didn't have them at all. But as they become a better donor and a better acceptor, you see how the gap drops. And if you reached the allele system, you would actually be at 0. You don't want to be at 0. You want this to be maybe 2 electron volts or some such value. And that suggests that having a captodative type substitution on that double bond will reduce the excitation energy HOMO to LUMO, the band gap, and you will get, if you choose them correctly, a colored material. Well, I will give you on the next slide an example of a molecule, if I manage to advance this, okay, which you can see as a perturbed ethylene. This is indigo. Well, indigo is very well known in India, of course. It is named for India. That's a blue pigment. This is the blue pigment that makes the blue jeans blue. It's a very stable compound, and it has been used for quite a while as an industrial dye. There used to be huge plantations of the plant from which indigo was obtained in India. And you can see that the structure indeed is just a perturbed ethylene. This amino group is a donor, this carbonyl group is an acceptor, and the same on the other side, acceptor and donor. So you could say, here we have done what we talked about. We took ethylene, we put captodative substituents on both ends, and from something that only absorbed around 200 nanometers, we now have something that's actually blue. It absorbs just exactly where we want the absorption to be for a dye for singlet fission. Unfortunately, this compound is not a good compound for singlet fission. Why not? Well, the triplet and singlet levels are in the right positions. Everything is fine. But there is a photochemical process. Actually, there are 2 photochemical processes ordinarily, but in a solid state, one of them is suppressed, which is even faster than the singlet fission. So it's an example where we are doing fine with the rate of singlet fission, probably, but we have a competing process that overwhelms the singlet fission process, and we get almost nothing in the way of triplets. The competing process is the motion of the hydrogen from a nitrogen atom to an oxygen atom. And you can do that on the other side also. The other process that is fast in indigo is cis-trans isomerization around this double bond, which occurs by twisting. Okay, so we were defeated here, but a chemist is usually not easily defeated. As you can see, you can prevent the twisting and you can prevent the transfer of a hydrogen by having substituents on the nitrogens. And this dye, which has those substituents present, so there are no issues with hydrogen transfer, and also no issue with a twisting of the central bond. This is now a rigid planar structure, is an industrial dye that has been known for a century, and it has the name Zibalacrot, that is German, a German, well, or Swiss actually, a chemist came up with this, where he worked for the company called Ziba, and Lack is lacquer in German, and Rot is red in German. So this is the red lacquer for Ziba. And this compound is about as stable as indigo. You could probably paint your car with this dye. It's so stable. And so one could say, okay, why not this one? Let's try this one. It also has this additional phenyl substituents. That's basically just for the ease of synthesis. All right, so what is the problem with this one? Why don't we have solar cells that use Zibalacrot? Well, it has a different problem. Maybe it's the same problem of a different kind. It's not photochemical reactions that ruin the performance here. It's a process that does not occur in solution, but will occur in the solid state. We have carefully eliminated the possibilities that ruined indigo, but we did not consider what might be a competition in the solid. In the solid, these molecules will sit next to each other. I will show you crystal structures in just a moment. What they can do is, instead of doing singlet fission, which should be possible because the triplet and singlet levels are exactly where we want them to be in this biradicaloid structure. The trouble is that even faster process takes over, and that's a transfer of an electron from one molecule of Zibalacrot to a neighboring molecule of Zibalacrot. So you get a so-called charge-separated state, and it is stabilized sufficiently that the molecules cannot return back to the S1 state of the chromophore and do singlet fission. And so you get trapped in a minimum, which basically ultimately just returns them to the ground state. And you do get some triplets because from this minimum you can get in a system crossing, but it's not more than 100%. Well, if it's not more than 100%, then it's useless for singlet fission. So that's two sad stories that we thought might work and didn't. And this is a very typical situation. When you search for new dyes, new chromophores for singlet fission, very often you find that yes, you can get the levels where you want them to be, and in this case, really very nicely, close to 1.1 and 2.2 electron volts. But another process intervenes, takes over, and makes your singlet fission give only very low yields of triplets. So this is what happened when we tried, in this paper it's described in great detail, we tried to work with Zibalacrot. Now, these are the two known crystal structures of this material, of this dye. And here is one view of one crystal structure. This one gives a rather low triplet yield, not by singlet fission, by inner system crossing. Here's the other structure, that gives a higher triplet yield, but still not more than 100%, again by inner system crossing. And if you take a different look, you can see that this one packs the molecules like this, the other one packs them like that. And what happens is the molecules just get closer when they are excited, and an electron is transferred to one to the other, and that's it. It does not go any farther to two triplets. What it ultimately goes is by inner system crossing to make just one triplet. That inner system crossing is pretty fast because the singlet and triplet states of that ion pair are almost degenerate. You can understand that because the overlap between the pi electron system of this molecule and that molecule is only very small. They just overlap here in the middle a little bit. And when you have that kind of situation, the singlet and triplet energies will be almost the same. So these are examples of systems that did not work well. I have here a few more structures that are of the same kind. Does somebody have a question?
No, that's okay. That's okay.
All right. And these are aminoquinones. This is a parabenzoquinone molecule which has two amino substituents. You would say that that is a very simple molecule, probably has been known for 100 years. But the fact is that it is basically unknown. So we decided to try to synthesize a few molecules of this kind. I have indicated here the results of computations for one of them. This is the method of calculation with a reasonable basis set and fairly high quality CAS-PT2 calculation. And the results shown here for the excitation energies are all doubled. This is the energy of for going into the S1 state. We even have the S2 state here. Here is the T1 state. There's the T2 state. These are excitation energies from the ground state. And the reason that they are doubled is that I show both the vertical excitation energy and the adiabatic excitation energy. The adiabatic is the one that really matters, that really tells us about the energy relation for vibrationally relaxed or geometrically relaxed molecules. And the numbers look pretty good. So for the triplet, the red, the adiabatic energy is just about exactly 1.1 electron volt, which is what we need. And for the S1 state, it's essentially exactly twice that much. So this might be an interesting molecule. But as I said, it's not known. One has to develop its synthesis. This paper is just a theory paper. And to start with, we made a molecule that had one more benzene ring. You see here, the red atoms are oxygens. So this is like parabenzoquinone. Here are the two nitrogen substituents. In order to avoid possible difficulties with photochemical transfer of hydrogen substituents on the nitrogens to the oxygens, we put methyls on the nitrogens. That blocks that problem. And then in order to avoid the rotation around the CN bond, we made this into a 5-membered ring. This is a carbon that carries two methyl groups. Well, this is a compound that was made once back in the 50s, and nothing was ever done with it. So we made it again, improved the synthesis, and started to look at its properties. The calculations did not look bad. This is the triplet energy, and but the singlet energy was too low. It was as you can see here, not twice the triplet energy, but we thought we'd look at the photophysics anyway, and I will not go through it in great detail. I'll just describe what happens very briefly. That's best seen in the plot that I show here, where time on a log scale is plotted horizontally. So you start with a tenth of a picosecond, 100 femtoseconds, and you go to 1 picosecond, 10, 100 nanosecond, and beyond. And what I show this way, vertically, is the population of the states after an initial pulse. The initial pulse is about 200 femtoseconds, and it causes a population of the S1 state. Well, that's not a big surprise. This is the absorption spectrum in the red line, but I will not talk about the spectra. Now we see a disappearance of the S1 state and appearance of the triplet state that's shown in purple. And then after it's formed, it lives forever on this scale. But there's a delay. The triplet state is not formed directly from the S1 state. It's formed from this intermediate. And when I first made this slide, I was not sure whether this is an Excimer or a charge-separated state or charge transfer state, or whether perhaps this is the biexciton that we would like to make. Well, now we know more. It is actually the charge-separated state. And so here we have another example why this compound is actually not useful for singlet fission. Here it is not a big surprise because the energies do not fit the rule that excitation of S1 takes twice the energy than the excitation of T1. And after all, this was just a model structure that had one extra benzene ring because that was much easier to synthesize, and we wanted to start to take a look at it. But this is a typical situation in many of the candidates for singlet fission. You make the singlet, of course, easily enough, and you even make some triplet, but you don't make it by singlet fission. This intermediate, the charge-separated state, is too stable, and it then decays, some of it directly and some of it by inner system crossing, to the ground state by return electron transfer, and that's it. So now we are working on the synthesis of the compound that does not have this extra benzene ring, because that one would, according to the calculation I showed you, have a much better chance to actually do singlet fission, and we're curious to see whether it does that. Even this is an interesting compound for spectroscopy and photophysics, because this looks like pentacene. This is deep blue, or like azulene, a deep blue compound. And like azulene, this actually emits from its S2 state. It fluoresces quite nicely from the S2 state, and it hardly fluoresces at all from the S1 state. So at least we get some interesting results to report, even though it's no good for singlet fission. It's just an example of the kind of structure that we are looking at. Well, this is enough in the way of examples of the kind of chromophores that are derived from a double bond by captodative substitution. Let's take a more general look now at the second issue, which was how do we pack these molecules in a crystal? Of course, nature will pack them for us, so we have limited control over that. Sometimes we can have more than one crystal form, and as you will, I'll give you an example of that. But most of the time, the control is very limited. There is a branch of chemistry which is called crystal engineering, where people try to modify the molecules in a way that would generate the kind of packing that they would like to see. And we're working on that now, but it's not an easy process. So what are the considerations that one has to develop when one wishes to determine what a good packing would be? That is not an easy matter, because to start with, you do not know whether you could just look at two molecules. Two would be the minimum that's needed for singlet fission, because you want to make two triplets and they have to reside on two sites. The issue is, how should be these two chromophores oriented relative to each other? And you do not have the certainty that considering just two of the molecules explicitly is sufficient. Maybe you need to consider three. Maybe you need to consider four. And of course, if you consider just two, you have a lot of possible geometries. You have, we showed it last time, you have 6 degrees of freedom, 3 translations and 3 rotations. If you wanted to consider all possible mutual orientations of 3 molecules, now you would have 12 degrees of freedom. And if you wanted 4, you would have 18 degrees of freedom. Well, very soon this becomes totally unmanageable. If you want to find an optimum geometry in a space that has 6 dimensions already, that's a problem. You're basically looking for all local maxima or minima, depending on how you define the function, of a function of 6 variables. So if you want to be sure that you find them all, you can have a grid where you put 10 points in each of the 6 directions, and then calculate at 1,000,000 geometries what the value of your function is. The function presumably is some measure of the rate of singlet fission. And then you look where the minima are or where the maxima are. Well, that's a lot of calculations. So you cannot really use a very advanced method if you want to do a million calculations. And that's the simple case. That's the case of 2 molecules. That's a search in 6 dimensions. If you wanted to search in 12 dimensions, you have a much bigger problem. So how do you go about this? Well, you could start by saying, let me use some sort of a genetic algorithm maybe, or some other such trick that would allow me to find the local minima. But then you will not have the certainty that you really found all of them. And so that's not so ideal. So let's take a look at the kind of function that you actually need to optimize. What will it contain? Well, if you want to consider just 2 molecules for the beginning, then you will have the following states to consider. You will have you can simplify matters by saying the only property that the molecules have that will be important for me is the highest occupied molecular orbital, the lowest unoccupied molecular orbital, the HOMO and the LUMO. I'll ignore the other orbitals because excitations from them will be at higher energies. And I really only care about S0, T1, and S1. All right, so then you will have the HOMO and the LUMO for 1 molecule on the left and 1 on the right. And you will generate from that excited configurations. Well, we don't need to worry about the ground state configuration. That will be fairly low in energy. We need to consider about those that are involved in the singlet fission process. So we could have the molecule on the right excited, as shown here, into the singlet state, or the molecule on the left excited, as shown here. The left is in its excited singlet state. and they will interact with each other. These two configurations will mix. If the symmetry is high, they may mix 50-50. If it's not so high, they will mix maybe 20-80 or something like that. And that is indicated by the solid orange line that indicates the interaction between them. And the matrix element of the Hamiltonian that describes that interaction will look something like this. We have the one configuration and the other configuration and the interaction Hamiltonian in between. So this is something we will need to consider. If these happen to be essentially degenerate to start with, after the interaction, they'll form a stabilized exciton and a destabilized exciton. But of course, these are just our starting points. Some mixture of this excitation and that excitation will be where we'll start when we absorb a photon. That's where the photon will bring us there. And now we have to consider singlet fission. Well, singlet fission will generate this exciton, where each molecule is excited to its triplet state. One of them has both spins alpha, the other has both spins beta. So overall, this is a singlet bi-exciton state. And as we said last time, going from a singlet to singlet is not going to be forbidden by spin symmetry, and so it can be very fast. Now you will have matrix elements that directly connect this configuration with this one, or that configuration with this one. And this is the so-called direct path. That matrix element, it's called 7 and 8 here, it looks like this. S0, S1 on the left of the Hamiltonian, T1, T1 to the right of the Hamiltonian, or the other way around. When you evaluate these matrix elements, you discover that they only contain 2 electron integrals. The 1 electron part of the Hamiltonian does not contribute. That's because there is too much difference between the occupancies on the left and on the right of the Hamiltonian. And if you apply the Slater rules and evaluate these matrix elements, you get a whole lot of zeros, and all that you're left with are these 2 electron integrals. This is true if you ignore the small overlap between the electronic cloud of the HOMO on one molecule and on the other molecule. That is probably a good approximation. Those overlaps are very small. If you do not neglect this overlap, you can still solve the mathematics, and you get formulas that cover maybe 3 or 4 pages. Whereas if you neglect that overlap, the formulas fit on half a page. All right, so this would be the direct process that can take us from S1 to TT, from the exciton, a mixture of these two, to the desired bi-exciton, where we have 2 triplets. Now, it turns out that in all cases that I know about in which singlet fission is competitive, where you are close to some local maximum of that rate function, this is essentially negligible. This is not an important process. What is much more important is a process that's mediated by going from the initial state to a virtual state shown here. That's an interesting virtual state. It actually is that charge separated state that I talked about before. One molecule has taken an electron from the other. This has become a radical cation. This has become a radical anion. This state is typically quite a bit higher in energy than the S1 state that you're starting with. And you might be tempted to ignore it because it's, maybe 1 or 2 or even 3 electron volts higher. But it is connected to the initial excited state by a matrix element, which is shown here, which now contains contributions from the 1 electron part of the Hamiltonian also. And those tend to be much bigger. And so if you now go through this virtual state to, let's go this way, to the biexciton state, well, you get a matrix element which is drawn here, X or Z. If you do it here, you get X, and here you have Z. And that is also large because it also contains contributions from the 1 electron part of the Hamiltonian. And you pay a price because you have to go through a virtual state. And so you have 2 matrix elements that you have to multiply. And you have to divide by the energy difference from here up to there. We're assuming that these are all at the same energy, all 3. But even so, this contribution, the mediated contribution or indirect contribution to singlet fission, usually overwhelms the direct contribution by a factor of 10 or maybe 100. So to a reasonable approximation, you can actually ignore that direct contribution. Now, the same sort of indirect mixing through a virtual state can also mix the excitation on molecule that's on the left with excitation with the molecule that's on the right. And that's shown here as well. Those are these green and blue arrows. And there's even an interaction between these configurations, which again only has 2 electron integrals and is basically negligible. The fact that these 2 charge separated configurations have only a small coupling element between them is actually interesting and important. This is a question that may be on your mind when I talked about the formation of these charge-separated states being competitive and causing trouble. Because you could say, well, if the 2 molecules are the same, both of them perhaps are Cibalacrot, then how does the system know which end should be positive and which one should be negative? Why don't I have an equal mixture of one and the other? The reason I don't have that such a mixture, which would have no net dipole moment, is that the matrix element that couples the 2, that mixes them, is weak, is small. And the degree of mixing depends not only on the size of that matrix element, but also on the energy difference of this configuration and that configuration. Well, I said a little while ago that they should be the same if the molecules are the same, but that's not quite true, because the environment, the other molecules in the crystal, the neighbors, do not have the same symmetry, and so they slightly stabilize one over the other. But because the coupling is so weak, that slight difference in their energies is enough to allow the wave function to be essentially completely this way or essentially completely that way. So the significance of this matrix element consists in its being so small that it allows this loss of the symmetry in the charge-separated states.
So, Joseph, just a question, quick question on this one.
Yes.
Very nice elaboration of all the terms. The last one, which you mentioned about, suddenly you considered the environment at this point. It was not a consideration before, But for this, you had to sort of bring in the lack of symmetry in the two molecules as it is. So is that lack of symmetry something to do with the initial excitation is anisotropic in the dimer?
Not directly. The reason why the slight difference in the energy of this configuration and that configuration is important is that it's the ratio of that energy difference and the magnitude of this matrix element that matters.
Yeah, I got it. I got it.
And if this matrix element is so small, well, then even a small difference of energies becomes important.
So then the S1, S0 configuration should also slightly be different.
Well, yes, but this matrix element is big.
Yeah.
The matrix element that couples them contains both 1 electron and 2 electron terms.
Yeah. Yeah.
It's large in magnitude.
Very large
so
in magnitude.
You would have to make the difference between these energies much bigger to get a complete dominance of one or the other.
Okay.
If you describe the mixture of two configurations, say this one and that one, or maybe this one and this one, if you describe them in simple terms, you can say, well, I have some coefficient multiplying the one that I have on the left, and then I have plus some other coefficient multiplying the one on the right. And if the two coefficients are both 1 over square root of 2, then the mixing is 50-50. And if one of them is a little bigger than the other, then the mixing is not quite 50-50. Maybe it's 40-60 or something like that. Right. And you can describe, and if you want, if everything is normalized and these two functions are orthogonal to each other, then you can say that one of these coefficients is given by cosine alpha, the other one is given by sine alpha. And alpha is some mixing angle. And you preserve the normalization and everything because sine square plus cosine square is 1. Well, what is the alpha that describes the mixing? Well, the alpha is described by an equation that says that the tangent tan of 2 alpha equals a fraction where you have on top the mixing matrix element, say this one, 9, or maybe this one, V, which is here. And at the bottom of the fraction, you have the energy difference of those two configurations. So if that energy difference is very small, you will get a large value for the fraction, and so on. So that's how one can understand why this hardly ever goes completely to just one side, whereas this one fairly easily goes completely to one side.
And the other question, there's one more question from a student who says, Konad, for the singlet fission process involving identical chromophores, what drives the formation of the D plus D minus state from S1, S0?
In the situation that I have described so far, this state is never formed. It's a virtual state. So it's a little bit like, say, Raman spectroscopy, where you, in the non-resonant case of Raman, you have a molecule, you send in a light beam, which is not absorbed because its wavelength is too long, but it will cause a temporal variation in the wave function of the molecule that's being irradiated. And if you describe that in the basis set of the molecular states, eigenstates, you will find that you have some contributions from all kinds of excited states. And so you can say that the molecule is perturbed. And then if the photon that is emitted, that is produced, and that you detect in the Raman spectrometer, and it has different energy because it uses a different vibrational level, that is obtained. That's an observable photon, and you have an observable final state, you have an observable beginning, starting state, but the virtual state that you have in the middle, where the molecule is perturbed but not quite excited into a stationary state, that's the virtual state. And so it's the same here. This is used only as a virtual state for going from here to here or to here. In the case of singlet fission, it's for going to here.
Okay.
However, the point that you're making is very important, because you may have an environment in which the charge separated states are not 2 or 3 electron volts above the initial exciton state.
Yeah.
Maybe the environment is very polarizable.
Right.
And or maybe it's polar and favors a charge development like this. This may happen especially in solutions. If you have a solution with a very highly polarizable solvent molecules or highly polar solvent molecules, they may actually favor this kind of configuration. You know, if you take the sodium chloride molecule and you put it in the gas phase, it will be covalent. It will not have 2 ions. But if you put it into water, where this is highly favored, well, then you get separation of sodium cations and chloride anions. And the same thing can happen also in the solid. If it happens in the solid, then this becomes an observable state. Then it's no longer a virtual state. It actually is a state that you can observe and that can live for so many nanoseconds. And we'll talk about that in just a moment. So the issue that you raise is a real issue. Any other questions about this scheme? If not,
not yet. So
okay.
Yeah.
Okay, so we'll go to the next one. Now, this ties very closely to what I just told you. Here are the 5 configurations that we consider: the S0, T1, D-, S1, and D+. We just talked about them. And we consider 2 molecules only, again, just a dimer. And we now follow the process of singlet fission. From the left, that's the beginning, to the right, that's the end. And I show 2 rectangles here. One of them has all the possible available states for molecule A, and the other one has all possible available states for molecule B. And in fat letters, in bold letters, I show which state is actually occupied. So these states are possible, but they are not occupied. This is the state that's occupied. If I have a solution, and these 2 molecules are far apart, as I indicate by having these rectangles separated by a white space, then they are independent. One is in the ground state, the other is in the ground state, everything is fine. Now, if a photon is absorbed, it will be absorbed by one of the molecules. The other one doesn't know about it, it's far away. So I have this situation. This molecule now is no longer in its ground state, it's in its S1 state. Well, that's why S1 is bold here. The other molecule is still in its ground state. If the molecules meet in solution, they will allow these to interact, and I have now one big square, because now A and B are one system. I can no longer say that they are independent and not know about each other. And I will then have the possibility that in this exciton that I just formed in that solution, I will have either molecule A or molecule B in the S0 state and the other one in the S1 state. And this mixture could be 50-50, but it could also be 60-40 or 20-80. This is what we talked about before. So we now have a system where the molecules can actually adjust their geometries by coming close to each other, being nicely parallel with each other, and interacting in the best possible way to form what's known as an excimer. And the excimer can live there for some nanoseconds, and it can do various things. It could dissociate back into two molecules and just return here, or it could emit a photon because it is stabilized relative to the separated molecules by some binding energy. That photon will typically be at a longer wavelength because not only is the excited state stabilized, but the ground state is destabilized because you have now pushed these molecules together in a way that's not favorable in the ground state. And so excimer emission is often observed in solutions, and it typically occurs at longer wavelength. And then you have a situation that can be reached in the solid, and that's shown down here, by absorption of a photon. Because in the solid, the neighbors are in contact from the very beginning. They don't have to wait to diffuse around and meet each other. They are already in contact. And so they are already in one rectangle as shown here. And when you absorb a photon, then you end up with this excimer or exciton. I should say exciton because the geometry in the solid initially is what it was in the ground state. This is a vertical excitation. But in some cases, they may actually develop into an excimer by getting closer to each other and changing the geometries in the appropriate way, the way that they would do it in solution.
That's why, just interrupting here, this excimer formation has been debated quite a bit experimentally in singlet fission, whether it is part of the singlet fission pathway or it's actually divergent or a branching part of the singlet fission. Yeah, so I think the reaction coordinate picture is missing in this particular diagram, of course. It's just the electronic state picture. But I guess the geometry changes would be the major ones to capture, to whether it goes to the excimer or goes regular, right?
Well, I would say that the formation that I show here is the vertical excitation. And so this is why I call it an exciton, not a excimer. To me, the excimer would differ from the exciton because it has had time to adjust the molecular geometry, the relative position of the two molecules and their orientation and so on. Typically, the best arrangement for the excimer can be reached in solution. It may not be so easy to reach in the solid state. There may be a barrier to its formation, or there may be some sort of local viscosity making it difficult to get the molecules into just the right position because they bump into the surrounding molecules and so on. So if I were to add that path to my diagram, it would go sideways and it would be somewhere here. It would look, the electronic state would look like this, but it would be a little more complicated. It would not have just two contributions. Typically, in the excimer, you have 1/4 of this configuration, 1/4 of that configuration, but you also have about 1/4 of this one and 1/4 of that one are the charge separated configuration. And so by bringing the molecules closer together to make the excimer, you make it energetically easier for the charge separation, and you can you lower the energies of these two configurations. You mix more into the final wave function. And as I said, it's roughly 1 to 1 to 1 to 1, roughly. Now, what could happen is in a system in which the polarizability of the environment is high and the stabilization of the charge-separated configuration is significant, you could go beyond the excimer and you could go to a state that's farther, in which you have actually completely separated the charges. And because the mixing between these two is a very small matrix element, whereas this one is big, these will polarize and you'll get either one or the other. And then you have this charge separated state. So to me, those would be side paths that are not on the main path to the two triplets that I want to be on. And whether they are very unfavorable or not depends on their energies. If the excimer, which is somewhere here, is only slightly stabilized relative to this exciton here, well, then it hasn't lost much energy, and it can still go and proceed toward the two triplets. If it is highly stabilized, that may be energetically impossible in the short time available, and it's a loss. You don't get the two triplets. And similarly, for the charge-separated state, if it is stabilized sufficiently and never can go back to something that can proceed to two triplets, then you're out of luck. You're just not going to get the two triplets at the end. So there are paths which I do not show here, and I could add arrows for them, which show loss mechanisms, decays that prevent the 200% yield of the triplets from forming, from being reached. And we have just discussed two. That would be from the exciton going to an excimer or to a charge-separated state, which would look like one of these, whereas the excimer would be all four of these. But there are others. For example, maybe this exciton that you form will emit a photon, fluorescence. Well, then you lost your excitation. You're no longer going to make triplets from that one. Or it could undergo a photochemical reaction. And this is true also for the excimer. The excimer could undergo a photochemical reaction, or it could emit a photon. The charge-separated state could go from singlet to triplet, and then you're gone from this path. You'll never make two triplets. Even the excimer itself could undergo inner system crossing. So there are many traps along the way that you can fall into and never make it to two triplets. And this makes the effort to actually produce a material that gives you 200% of triplets, that is quite a struggle, because there are so many ways in which you can get lost from the path. So now let me return, if there are no more questions, let me return to following the path. So I have just told you that, yes, we have, I agreed with what you proposed, that we have side paths to excimers and charge-separated states. I've told you what their wave functions look like. And if they don't involve a great loss of energy, maybe they are innocent. Maybe they don't kill you because you can come back. So they have a potential for being bad, but they are not necessarily bad. But there's no reason why they would be good. However, now let's consider the actual step of the main step of singlet fission, where you go from the exciton, which will contain some small contributions of these charge-separated configurations, and we go to double triplet, to the biexciton. sorry, biaxiton state. Well, that is shown here. Now we have both molecules such that the T1 state is occupied of all the possible states on molecule A and also on molecule B. So this is what we want. Is this the singlet biaxiton? We're not quite yet at two individually separated triplets, but we are well on our way. As I told you, there are two paths to go from the exciton to the singlet biaxiton. There was the direct path, because there is a matrix element that takes you directly from here to here, but it's very small, and usually that path is negligible. The other path uses these charge-separated states or configurations as virtual states. And the importance of these virtual states, or the degree of help that they give you for going from here to here, is a function of their energy. If they are very high in energy, it will not be much help to use them as virtual states. Because remember, you have to multiply the matrix elements for going from here to here by the matrix element for going from here to here, and both of them can be large, but then you have to divide by the energy difference between these configurations and those configurations. And so if it is 10 electron volts, you'll be dividing by 10. If it's only 1 electron volt, you'll be dividing by 1. That's 10 times better. And so in that sense, the availability of low-lying charge-separated states can be very helpful to increase the rate of singlet fission. And so on the one way, you could say it's a danger to have these states available. If they can actually be occupied, become real states. And simultaneously, it's an advantage to have them low, but not so low that they would actually be occupied. Now, of course, once you say that you can occupy these charge transfer or charge separated states, you open another Pandora's box, because these states, if they are occupied and live for some time, some picoseconds or nanoseconds, they can do all kinds of other mischief. They can do inner system crossing, they can, and so on. So you just open more paths for a possible loss of the traveler from where he started or she started to where you want them to go.
This is exactly the question one student asked from YouTube, listening to your lecture right now. Alfie Benny, he's from ISA Thiruvananthapuram. So he asked, Professor Michl, could you describe that CT states, how to predict CT states which could be just the intermediate to singlet fission, or they could act as trap states? How do you predict that?
Well, to do that, you need to know the properties of the environment. You need to know how much it stabilizes the charge transfer state. And calculating their energy is not easy, because it would be easy in vacuum, but you're not in vacuum in the system, you are in some solid. And so you cannot just use a dielectric constant of 1. And what to use for your dielectric constant is not so easy to calculate. And moreover, you could even ask whether you have whether it's really a constant in various parts of the space around the molecule. So there are procedures to do that. Grozema developed one, and you can do that, but it's not an easy calculation. I mean, it's not like anything as easy as what I'm talking about here. So, yeah, it's troublesome. All right, so now we have made it all the way to this singlet biaxiton. The way that I indicate here from the singlet biaxiton to two separated uncorrelated triplet states is schematically indicated by more than one arrow. because it involves more than one step. There are cases that have been studied in enough detail that one can propose roughly how it goes, but it's not obvious that it always goes in the same way for every material. But sort of typically, to have something to think about, you could say that there are actually 9 microstates available to a system that's described in this orange rectangle, because each triplet has 3 sublevels. And so 3 times 3 is 9. And description of what's happening requires a matrix that's 9 by 9. If you consider the simplest case in which there are minimal interactions or no interactions between the molecules that would be sort of relativistic in their origin, they depend on spin, then this 9 by 9 matrix is block diagonal, and you have a 1 by 1, 3 by 3, and 5 by 5 blocks. And you can call them singlet, triplet, and quintet blocks. And in reality, you will always have some magnetic field, and that will produce Zeeman terms that will be off diagonal and will couple these things. And what's always present also, and usually more important, unless you intentionally introduce magnetic fields, is an interaction of the magnetic dipole moment that's due to the spin of an unpaired electron on one molecule with the spin of the magnetic moment due to the spin of another electron on the same molecule or even on a neighboring molecule. Usually on the same molecule is much more important. This is this spin dipole part of the Hamiltonian is very well known to electron paramagnetic resonance spectroscopists, because when they study triplet states, these are exactly the terms that they deal with. And they are responsible for the zero field splitting in EPR spectra that you see for triplets or for higher multiplets. And they can be described and evaluated, and in a crystal where molecules are oriented, you have to consider the orientation in these interactions, and it's all relatively complicated. The presence of the off-diagonal elements that are introduced by these interactions, these spin dipole interactions, or the so-called D and E tensor of EPR spectroscopy, as well as the off-diagonal elements that are introduced by magnetic fields, which you can introduce intentionally, or which are present because of the magnetic field of the Earth has not been shielded or something like that. They will mix the states that are in the 1 by 1, 3 by 3, and 5 by 5 blocks. So if you start as you do in singlet fission, in the pure singlet, you are starting in that one block that is 1 by 1. But the existence of these coupling matrix elements that are off diagonal that couple you to the 5 by 5 block, and then later couple the 5 by 5 block to the 3 by 3 block, means that this is not really an eigenstate of the system. So it develops in time. And you can describe it using density matrix theory, and you discover that you would expect that this singlet state develops into a quintet, and that has actually been observed. People have done the EPR spectroscopy on that time result and seen the quintet. And I think in one case, the next step also has been resolved, which is going to the triplet. So you have 3 different species instead of just the singlet that I show here. And it is not clear whether all 3 of them can dissociate, overcome the binding energy of the singlet biexciton and dissociate into 2 independent triplets, or whether only 2 of them can, or only 1 of them can, and whether it's the same for every material. This part of singlet fission is still, to a large degree, a mystery. Unfortunately, it is an important mystery because, again, as you proceed through these various steps, you can have losses. You can have side paths because, for example, when you get to the triplet, that is not the lowest triplet of the molecule. That's the 3x3 block. The T1 state is lower. And so you could go to that fairly rapidly by internal conversion. And that would be a loss path because out of 2 triplets, you're making just 1. And so the decay paths that can start from these combinations of 2 triplets in either the 1x1 or 3x3 or 5x5 block are bothersome. They can reduce the overall yield of what you want. So that, in summary, I must have talked about this slide for 15 minutes. That is how complicated the singlet fission process really is. And we have not even focused on all of the side processes that compete. I just described the main path, in the liquid this way, in the solid that way. And we did mention these side processes that can reduce the yield from 200% to lower values, but we didn't really discuss them in detail. All right. Now, I don't know if there is much time left. It's now 8:30.
Yeah. So, do you have how much material do you have, or?
Oh, I prepared quite a bit. I can keep going for quite a while.
Yeah. Well, I think maybe if you would like to cover some significant aspects and then maybe conclude, and then we can take questions. Because there will be a lot of questions from this talk, and we would like all the panelists to ask and students to ask. So
maybe I think this slide is important. Probably we can go a little bit about here. After this slide, we can begin the question answer.
Whatever, Joseph, however you want to summarize or whatever.
Okay. So I'll start going relatively rapidly, and you stop me when you've had enough.
That's not going to happen because we are loving it. So that's yeah. Go ahead.
All right. So now let's ask the question. I know that I need to evaluate the rate of the step that goes from the S1 state to the TT state, from the monoexciton to the biexciton, as a function of molecular arrangement in the crystal. I know I also should do the same thing for all competing processes. I do not know how to do that. That's what we're working on. So I won't talk about it. I will only talk about looking at the rate of the singlet fission itself. Now, that's something I can measure. And so it's a meaningful quantity to calculate and compare with experiment. Now, I want to do this for only 2 molecules. Even that is a search in a 6-dimensional space. We're now working on trying to do it in a 12-dimensional space, possibly even 18-dimensional space. But that's a considerable mathematical problem. And we haven't solved it. We're working on it. I will not talk about it. Let's just talk about 2 molecules. You could, in a way, study dimers, and many people do. And if you study dimers, you could study them even in solution, And then this is not an approximation. You only have 2 chromophores. So let's take a look at what the situation is like for 2 molecules being considered. This is the expression for the matrix element T that describes the, that goes into the Fermi golden rule expression for the process of singlet fission. Remember, I gave it to you last time. We had the Planck constant to minus first power, and then we had the square of the matrix element, the electronic matrix element, and this is it. That's this T. And then we had a term that had the density of states in it. So let's calculate the T, and then let's use something like Marcus theory to take care of the density of states problem. Now here is the matrix element. This is how it is defined. This is what we talked about before, just a couple of slides ago. If you do the evaluation and make the approximation of neglecting the overlap between an orbital on one molecule and another molecule, then you get the following result. It will have the direct term shown in red here. Well, you can see it's the direct term. It's the configuration that you have, that you're starting with, and the configuration that you're going to. And that's the one which is going to be neglected. It's very small. Now, there may be situations in which it is not negligible and it is significant because this other one is very small. But I don't know, maybe there is one experimental example, rubrine, where this might be the case, but it would be, it's not typical. The typical case would be one in which this is negligible. This is the mediated case. Well, it has the form I told you it has. This is the first matrix element that contains 1 electron integrals multiplied by the other one that contains 1 electron integrals and divided by the energy difference that's needed to make a cation anion pair out of the exciton. And so you have something here, something very similar there. And once you make the cation on the molecule on the left, and once you do it on the molecule on the right, this is the mediated term. So you need to evaluate this term not a million times. That would not be a grid that's dense enough. You actually typically need something like maybe 500 million times. So it's a very large number of calculations. You cannot afford to evaluate this exactly because you're doing it so many times. So what do? Well, you introduce neglects that you think are physically reasonable. I already told you that the intermolecular MO overlaps are neglected. You also introduce zero differential overlap. I will not explain these approximations in detail because we're now going just very rapidly.
Yeah.
And those of you who are familiar with the old-fashioned semi-empirical theories of quantum chemistry know exactly what this is. You expand each molecular orbital, the HOMO, which I call H, and the LUMO, which I call L, in an orthogonalized valence atomic orbital basis set. The atomic orbitals are called mu and nu. Then you say that the element of the Fock operator, the ground state Fock operator, between the atomic orbital mu on one molecule and the atomic orbital nu on another molecule is equal to the resonance or hopping integral. Then you use the Mulliken approximation to evaluate the resonance integral between two orbitals that are located on different centers, different atoms. And then you say that the resonance integral is proportional to the overlap integral. Well, this is basically the extended Hückel theory that uses that approximation, or the Wolfsberg-Helmholtz approximation. And then finally, you make a very rough approximation, which would not really need to be done, and we're now going to remove it actually in the work we're doing. And that is that you say, all right, as long as the two molecules touch, it does not matter how they are oriented relative to each other. It still takes always the same amount of energy to take an electron from one and give it to the other. That's an approximation. And there are some numerical results for testing that. They say, well, it's not really a terribly good approximation. You may have 1 electron volt energy for this arrangement and 1.5 for that arrangement.
Right.
And still, whether you divide something by 1.5 or you divide it by 1, and then take a square, because it's the square of this matrix elements that goes into the Fermi golden rule, okay, it will make a difference, but it's not going to take something that corresponds to a local maximum and make it into something that is a local minimum. It's not going to change the rate that you calculate by many orders of magnitude.
Right.
So using this set of approximations, you can now express the square of the matrix element that you need in the way that I show here. And I see that these arrows have shifted. Okay, does not really matter much. You can see that there's analogy between this expression here with that division and this first term, and then this expression here with that division with the second term. So an important thing is that it's a difference of two terms. And the terms may look complicated, but actually not complicated. There's a constant that contains some universal constants that goes in front. Well, that's not a big deal. If we are looking for the local minima and local maxima, that will just multiply them by a constant. The goal of this calculation is not to get the rate of the singlet fission. The goal is to get the geometries at which the rate is optimized.
Mm-hmm. Okay.
So now, what are these terms? Well, each one of them is a product of two sums. One sum and the other sum.
Yeah.
And then it's divided by this energy difference, which we said will arbitrarily set to be a constant, say 2 electron volts. If you make the same error for each term, all you're doing is just multiplying this by a constant. And again, that won't change the geometries at which you find your local minima or maximum. Now, what are these numbers here? Well, the coefficients C are simply the Michl coefficients of the HOMO in blue or the LUMO in red on that you find on one and the other molecule on atoms mu and nu,
Right.
and you summing over all pairs of such atoms.
Right.
And L, that just is there in order to indicate that the red is for the LUMO, and this is the Michl coefficient on the HOMO. And you can get those without much trouble very easily. And they are the same for the two molecules, no matter how they are oriented. And the product of the coefficients is multiplied by the overlap. Well, calculating the overlap integral between two basis set orbitals is the simplest evaluation that you can do in integrals. And you can do that many millions of times. That's not a problem. And then you have a summation over every atomic orbital on molecule 1 and combined with every atomic orbital on molecule 2. So mu is always on one molecule, A, and nu is always on the other molecule, B. So you have this kind of product, and then you have, this kind of sum of products, and then you have this kind of sum of products. And those are only different in that now you take both of these coefficients from the LUMO. And here you're doing something very similar. You again have, in this term, you have one coefficient from HOMO and one from LUMO, and here you have both from HOMO. Well, a computer can evaluate this in a few microseconds. And so if you have a day or of computer time, you can evaluate this expression for, you know, 500 million geometries. It's not a big deal. So if you do that, now you have the function t squared, and you are in 6 dimensions. So you can actually afford to ask the computer to look at all the points in the grid that you have calculated. For each point on the grid, you have evaluated t squared. And you can ask, if I go from a point to the neighbor and the next neighbor, does my function continue to increase or drop, or is there does it go through a maximum or a minimum?
Right.
And so you can actually afford, in a very short period of time, on a standard computer nowadays standard, it would have been hard 30 years ago, but nowadays it's easy. You can actually search the whole 6-dimensional space for the local maxima of t squared, and therefore the local maxima of Singlet Fission.
Okay.
Now, there is a catch here. I said the whole 6-dimensional space. Of course, that goes from a 0 angstrom separation between the centers of mass to an infinite separation.
Right.
But I don't need to look in regions where the molecules don't touch.
Okay.
So I can just look for a while and stop when they are 5 angstrom apart or something like that, and then I'm done. So I'm not looking through an infinitely large space. I'm looking for a subspace that has finite dimensions.
Okay, so I think, Joseph, I guess we are dropping in numbers at this point in terms of the audience. So maybe we can conclude in a, so that we can take some questions. I think I would like people to ask questions. Maybe we can take questions here as well.
Yeah, okay, let me just tell you a few words about,
absolutely.
About this slide, because this expression is complicated if each molecule has many, many atoms in the pi system.
Right.
But let's take an example of ethylene. That only has 2 atomic orbitals on the molecule. And so suddenly that big long expression
collapses,
becomes just this.
Yeah.
Because I know what the coefficients are on my ethylene.
Right.
And so now I have an expression that I can translate into a sentence that tells me what is favorable and what is not favorable when I work with ethylene. And
Sure.
you can see when this is going to be big and when it's going to be small. If these 2 terms are equal in size, then the difference is 0. I want one of these terms to be small and the other one to be big if I want a large square. And these terms are just products of overlaps. Well, I can look at the picture of 2 ethylenes and I can see that the overlap between these 2 is large.
Right.
This is not so big. But I also see that this overlap and that overlap are the same in magnitude as these 2 by symmetry.
Right.
So I can immediately say I get 0.
Yeah.
So you get a 0 matrix element if they are stacked.
Perfectly stacked.
You just want to have one of them big and the other one to have a 0. Here you have distance that's large, that overlap vanishes, and so this is much better than that. This means you need to do a slip stack geometry, not a completely stacked. Or you can do something like this, where this orbital nicely overlaps with both, and the other one doesn't overlap with either one. Or here, this orbital overlaps with both on the other molecule. This one is too far away to overlap at all. So you can make simple statements for ethylene. And it turns out that you can generalize this to other molecules also and make simple statements about how the molecules need to be oriented in order to get a large value for the matrix element square. Okay. And what I have here is just some comparisons with exact calculations and the approximate ones showing that they give the same pictures. Let's skip through that. This is just a few more examples. Here is something I could discuss at length, because you don't want to consider all possible orientations of those molecules. You have to exclude those in which the molecules will interpenetrate,
Right.
because you cannot regain them. And so you have to do that math. Here are some examples, and here for a variety of molecules are predictions for a whole bunch of different geometries that are favorable. Here are some experimental results. Here is a piece of evidence that I need to mention before I finish, and that is that the approximation of using just a pair of molecules is not really adequate. There are two crystal forms of this molecule, diphenylisobenzofurane, and one of them is 6 times faster in singlet fission than the other. And they are so similar, as you can see here, that every molecule has the same environment in both crystals. Environment being the nearest neighbors. It's only the next nearest neighbor that's different in the two crystals. And so that next nearest neighbor is so far away, you can see the difference here. You have, these are in the same relation of those. But the third one is in a different relation to these two than to those two. And so this one is so far away from that one, they have no direct interaction. It's that this molecule mediates the interaction between this one and that one. And these three body terms will have to be considered, and that's what we're working on now. That's why we think we need at least 3 molecules and maybe 4, not just 2. So this is a sort of a sobering note at the end, and I think we can stop at this point.
Oh, okay. That's very nice. Thank you, Professor Michl. This was very, very elaborate and descriptive, and I like the ending, including a 3-body term, because that is not very conventional. So I guess that's something that you are really actively working. I think I will take first a question from a student, Konad Mujumdar. So Konad is asking 2-part question. What role can molecular structure play in movement of a singlet TT state to a quintet TT state, or is it purely statistical? That's the first question. So let us take that question first.
Well, the terms that cause the conversion of the singlet to the quintet are these. Those are the elements of the DE tensor from EPR spectroscopy and any magnetic field effects. So you could use a magnetic field in a particular orientation to enhance the rate of this transformation, and you could calculate. That's a fairly difficult calculation. These elements of the D and E tensor, and look, nobody has done that to my knowledge. Look for some rules that would tell you how molecular structure will modify these terms in order to make them large, so you can go and increase the rate of this transformation. That would be a nice research project.
Right. Okay. And Konad, do you want to ask the second question, or should I ask it? It's a dimer question, so you can ask if you want.
So, can you hear me, sir?
Yes,
I hear you well.
Professor Michl, I was wondering, for dimers where we have individual chromophores linked through us, covalently linked, how important is it for the HOMO to be localized on the individual chromophores? What happens if you have a delocalized electron density over the entire system? That would break the idea of a bichromophoric system. So what would happen in such a case?
Are you probably talking about covalent attachment without direct conjugation, maybe through some alkane chain or some saturated ring or something like that?
No, like we have dimers, no, with phenyl spacers or ethylene spacers, like 2 pentascenes covalently linked to a phenyl spacers, something like that. Hello.
Well, the best orientations for that have not really been worked out to my knowledge. People have done calculations of rates for specific geometries that they knew they had in their hands, maybe from X-ray structure analysis of the dimers. But a general treatment of the kind that I described here for molecules in a crystal, even in the pair approximation, to my knowledge, is not available. So it's difficult to give an exact answer. The delocalization itself does not make a whole lot of difference. You could have a factor of square root of 2 or something like that. If you go and start in S0, S1 on the one hand, or in a one-to-one mixture of S0, S1 with S1, S0 in the other hand, on the other hand. That would not make an order of magnitude difference.
Okay.
Okay. Thank you, Konad. Arup, can you unmute yourself and ask the question, and then Professor Oyan Datto will ask.
Yeah, am I audible?
Yes.
Yeah. So yeah, my question is on the very initial part. Then when you mentioned that the importance of the extracting the charges at the interface. So in that context, how important to look into the lifetime of the free triplet, and is there any rational way or analogy that how the triplet lifetimes are related to the molecular orientation, how the molecules are packed to each other? So is there any rational analogy that triplet lifetimes can play an important role to extracting out the charges, or is there any such importance of that?
I'm sorry, I did not understand the question.
The question, okay.
The sound was not very clear.
Okay. I'll paraphrase the question. What Arup is asking is a two-part question. One is, he's asking what is the role of the triplet lifetimes in your charge extraction process at an interface for the singlet fission to take place. And the second part of the question is there a role of packing in determining the lifetime of the triplets?
Well, the lifetime of the triplets depends to a large degree on defects in the crystal structure. Any trapping center, maybe grain boundaries, things like that, can be very detrimental. So you generally need to worry about traps. The triplet lifetime, in the ideal case in which you don't have defects and traps and oxygen and things like that, is dictated by the inner system crossing to the ground state, assuming that their concentration is so low that you don't get any triplet annihilation. And those are in the hundreds of microseconds, typically. So if you put in heavy atoms into the molecule, for example, you will enhance spin-orbit coupling and you will shorten the triplet lifetimes. If you introduce low-lying and pi star states frequently, that will shorten triplet lifetimes. So there are certain structural features that would be bad, but they really are the same as they would be in solution. And that is, I think the two that I mentioned are the best known. Yeah. So that would be the answer to your second question.
Okay.
Or maybe the first, to the first question, you were asking how does the packing in the crystal affect the lifetime? It probably does not affect it very much. It could affect the rate of travel, the rate of hopping from one molecule to another molecule. And that is important because the distance that the triplet will travel depends on how long it lives, but also on how rapidly it makes these hops. And in general, people are used to dealing with singlet excitons, and they have a much shorter lifetime. So they are less prone to trapping by defects or being destroyed, quenching by defects. But they also generally travel a much shorter distance because of the short lifetime. They just will emit a photon, if nothing else, before they get very far. So the triplets usually are not considered to be problematic in the sense of not being able to travel a reasonable distance. People are used to handling singlet excitons where it is much more of a trouble.
Okay. Okay. Thank you, Professor Michl. I will request Professor Ayan Datta to ask his question.
Yeah. Thank you for the wonderful two tutorials, Professor Michl. So I had a question in terms of trying to think of the same problem from a physical chemist viewpoint. See, I mean, the fact that you have the charge transfer state, which is typically higher in energy than the ground state, other than for very rare deuterionic structures or something. Now, for the cases, I mean, the charge transfer state, as even trying to think
Before you continue, it's not that the charge transfer is much higher than the ground state. What matters is that it is higher than the excited state.
That's right. That's right. That's
the S1 state. Yeah. Okay. Please continue.
S1. Yeah. So so of course that will also depend on the polarity of the medium, right? So I mean, has something been worked out in terms of the dielectric constant in the solids? Because to estimate the dielectric constant of the solid medium, that also depends on the packing orientation of the molecule, the local structures. But in terms of the position of the charge transfer states vis-a-vis the the local dielectric constant of the few molecules which are interacting. Can one think of a simple model? I mean, other than computing it, because then every molecule is a separate computation.
Yes, this is a problem that we are actually struggling with right now. It is clearly unreasonable to ignore the dielectric constant, and it is not simple to decide what its value should be, because it's really sort of a, as you pointed out, a local property. And you should probably have a different dielectric constant in different places. But there is this procedure that Grozema developed that includes these interactions in an approximate way, but fairly reasonable way. And overall, the effect is not huge. It is, as I said, you multiply the dielectric constant by 2 while you change the rate by a factor of 4, because it's the square of the matrix element that matters. And if you are trying to predict the rates of Singlet fission, that's not very good. You will not have a terribly nice correlation. But if you're just looking for the favorable geometries as opposed to the unfavorable ones, well, then a factor of 4 is not very important. For example, the slipping that I said you need to have of the 2 ethylenes. Well, okay, so that may make a difference between telling you should slip by half an angstrom or by 3/4 of an angstrom, depending on what you assume or what you calculate for the dielectric constant. That's not terribly important, because to start with, you have a certain width that was on one of my transparencies actually. The maxima that we find are not terribly sharp. They have a certain width. And so if you are not exactly at the very best geometry, but slightly to the side, again, you may lose a factor of 2 or something, but you're not losing a factor of 1,000. And if you try to use crystal engineering or the synthesis of covalent dimers to achieve a particular structure, you will have a hard time getting exactly the structure that you want. You will be a fraction of an angstrom off here and there. So the question that you're asking is important, but I don't think it's overwhelmingly important.
Thank you.
I request Professor Ravindra Venkatramani to please ask his 2 questions.
Yeah. Hi, Joseph. Thank you for the tutorials. It was really useful for me. I had like a couple of questions actually. One was a very general question about the definition of these bound triplets, the T1, T1. So it seems to me that, I mean, like the definition is somewhat contradictory because you would like these triplet states to maintain their identity and yet couple to each other strongly. Is this making sense actually from the point of view of the definition?
I don't want them to couple strongly because then they will never diffuse apart.
Right, but then you would still like them to, you would like the singlet to actually populate these triplets. So in that sense, I mean, like both these triplets have to somehow, be coupled to each other. Otherwise, I don't see how one can possibly create these triplets. They have to be created simultaneously in some sense. So the coupling has to be.
You are certainly right about the 2 molecules having to interact. But the matrix element that tells you how rapidly they'll go from the singlet exciton to the biexciton is very different from the matrix element that tells you how strongly the 2 triplets are bound to each other. So you could have one of them small and the other one big.
I see. So in a sense, the factor that couples these systems together need not be the same electronic configurations or orbitals.
Yes, that's right. The nature of the interaction is not the same. The way that I described it, you have the dominant contribution to the singlet fission rate originating in a matrix element that I went through in some detail, and it has a product of 2 matrix elements that contain 1 electron integrals of a certain kind that involve HOMO and LUMO, divided by that energy difference to the charge separated state from the S1 state. And that is quite different from the terms that I believe dominate the binding energy of the 2 triplet molecules to each other.
I see.
Because the reason why the 2 bind to each other in the solid, in my opinion, and this may not be widely shared, but that's what I think, has to do with the fact that if the 2 triplets are next to each other, the dominant configuration, which is T1, T1, can interact with charge separated configurations like that I called a D plus and D minus, where you have a cation and an anion, or an anion and a cation. And those are of a relatively low energy because you're not separating charges very far apart. The 2 molecules touch each other. They are typically right next to each other. And so, yes, you're separating charges, but you're not separating them very far. Whereas if you have the 2 triplets diffused from each other, now there are 2 free triplets, they will be described as T1 on one and T1 on the other, but the stabilization by the interaction of charge transfer configurations will be much smaller, because now a charge separated state would describe a very much larger charge separation, and so it would be much higher in energy. because
Right.
now the two triplets are no longer next to each other.
That's right. Yeah.
And I think this is the origin of the small binding energy. The typical values that people come up with are some tens of milli-electron volts. These are not large numbers.
Yeah.
Yeah.
So the physical origin of that attraction or interaction, if you will, or coupling, if you will, is quite different from the nature of the coupling that's actually responsible for the event of biexciton formation.
I see. I see. Okay, so that clears that up. I had another technical question actually with regards to your calculation of these scores, the T scores that you showed when you're trying to optimize the different geometries, when you're calculating geometries.
Sorry, I did not understand the word that you used. You said schools or scores?
The capital T scores. The capital T, you're talking about the rates, right?
Yeah, the rates, the singlet fission rates that you're trying to optimize. So those are your scores, right? When you optimize geometries, you would like to optimize those scores, right?
I don't understand that word still. Cores?
Scores.
No, it's scores.
Scores.
Okay, I will use a different word.
SCORES. Scores. Values. I think he just wants to.
Yeah. Okay. Anyway, so it's so the singlet the rates.
The rates.
So while you're computing those rates, you know, the overlap integrals that you compute, they should have some kind of a resonance contribution, right? In some sense, because essentially, I mean, like, you know, if you're looking at the particular coupling element for a geometry, that geometry might not be the optimal geometry at which you would like to compute these matrix elements. So I was wondering, is that a problem when you're actually computing or carrying out these geometry optimizations to get optimal rates, singlet fission rates that you compute, for example?
I'm not sure I understand the question. I can see two things that you may be asking about, and I don't know which one it is. So
let me.
The coefficients that you're talking about are the molecular orbital coefficients that describe the HOMO and the LUMO orbital?
No, not at all. So in fact, if you go back to Marcus theory, in Marcus theory, electronic coupling element is computed at the crossing point. So that's a resonance condition, right? So the electronic coupling makes sense only when the donor and the acceptor are resonant, for example, right? So similarly, when you compute your overlap integrals, the two states that you're considering should have some resonance conditions, right?
I see. I understand now what you're asking. So this has to do with the density of states term in that Fermi golden rule expression.
Absolutely. You're right.
Okay. And I haven't really talked about that at all. What we do is use the simpler form of Marcus theory, in which you have an electronic matrix element that we evaluate at the very large number of geometries, millions or tens of millions of hundreds of millions of geometries, and then they contain the this is the simplest form of Marcus theory. So they contain the reorganization energy, which we calculate sort of once and for all from the molecular or for the molecular pair. And then they contain the exothermicity or endothermicity. And that's where you get the Marcus parabola.
I see.
The position that you are on. So it's a very primitive treatment that we are using.
I see. Okay. Thanks a lot.
Okay. Are there any other questions for Professor Michl? I have a couple of students also still remaining. Any student questions? You can unmute yourself and ask the question directly to Professor Michl. Okay. Well, it seems like a long session today. People are a bit weary, but I guess I would like to. Ayan, you want to say something? No.
No, I just want to thank Professor Michl.
Yes.
I mean,
Yes.
yeah. Thank you ACS, thank you IISC, and thank you TIFR. Thank you Satish, thank you Jyotishman, and for getting the experts. And please do visit us in India.
Yes.
When you are here, Professor Michl.
Well, thank you very much. I would like to do that. I visited India once and Nepal once, and it was a very enjoyable experience both times. And so thank you very much for your kind attention. It was wonderful to have an enthusiastic audience when I talk about one of my favorite subjects. So this was a very nice opportunity. Thank you.
Thank you, Professor Michl. And I'd like to mention Professor Datta is joining from Indian Association of Cultivation of Science, Kolkata. So if you visit Bombay, Kolkata, Bangalore, those will be the places you should.
Yes, I have not visited Kolkata before. I did spend some time in Bangalore.
Okay.
Yes. Okay. Went to the
so I think Kolkata and Mumbai remain. So I guess you should come to our institutes. Definitely.
I went to first grade when I was a little kid with a classmate who was from Bombay.
Okay.
So that's as close as I came.
First grade. Okay. Thank you, Professor Michl, once again, and thank you all of you for sticking around from 7:30 in the morning. I just wanted to mention two things. We have in this series upcoming talks by Professor Seth Marder from Johns Hopkins, who's going to talk about doping in polymers. That will be in February. And in March, we are having Professor Gregory Engel from University of Chicago talking about coherences. So spectral signatures of coherences. So those are some of the upcoming sessions. So thank you very much. And I want to thank ACS again for this. Okay. Thank you, Professor.
Thank you, and enjoy your day.
Thank you, Professor Michl.
Thank you.
Thank you, Vivek.